Okay, we're going to continue our discussion of linearizing nonlinear objective functions and constraints. But really, in our previous problems, this linearization or conversion to a linear program allowed us to preserve the formulation so that we still get the same results. In this particular case, we're going to be discussing how do we approximate nonlinear objective functions. And in this case, this approximation will not give us a problem that is an exact representation of what we started with. All right. We're going to begin with an objective function. So let's say we have our minimize f of x subject to some constraints where x is in a constraint set. We're going to require that our function f of x has a property where it's a separable function composed of, let's say, fi of xi that are convex. And so what do we mean by that? So instead of just writing f of x, we can write our optimization objective function of f1 of x1 plus another function of x2 plus another function of x3. And this is going to go on across all the dimensions of our decision variable x. Now, the idea that we're going to take is that we can approximate each of these f of I functions in terms of their variable. Using a set of linear equations. So in order to do this, we're going to use a particular property that we had mentioned before that's associated with convex functions. So you might recall a function is convex if each tangent line lies below the function itself. We can visualize that through this example. So let's say we had this function here. This will be our f of x function. And we can take a series of tangent points. So maybe here we take a tangent point here, here, and here. We can even name these. So this will be f of x1 tilde. So that's the first tangent point. And then we can talk about the value at the second tangent point and the value at the third tangent point and fourth. Okay. So here goes x4, x3, x2, and x1. All right. So at each of these points, we're going to draw a tangent line. I'm going to see if I can draw the red tangent line. Jeeps. There we go. So here goes our first tangent line. And I'll do this for point 1. Right. And so, coincidentally, that's going to the x2 point, but maybe we'll adjust it so it doesn't look like that. But. All right, so we got our first tangent line. And we can see that this tangent line at x1, right, so this is line 1, it's below our function f of x at all points, so it's supporting it. And this gets repeated for each of the tangent points when we draw that tangent line. So I'm going to draw a bunch of these so we can see all 4. There's another one. So that's the second line. Oops. And we'll do the 4th one. Okay. Oh, that worked out nicely. Alrighty. So what we see is each tangent line supports our function. These lines can then also be written in sort of as a linear equation, right? So picking out line 1, right, or just an arbitrary line I, we can represent it as y equals mx plus b, right? And maybe we'll put I to indicate the index. Now, for this particular function, and again, this is the ith function in terms of the xi. So there's all sorts of indices getting thrown around that I'm dropping, but understand this for one decision variable, the ith decision variable. All right. Now, how do we use this? Well, what we can see is each one of these tangent lines is a lower bound on our function. Okay, so that means if we look at fi of xi, it has to be greater than, and I'm going to write out all the index here. So mi1 times xi plus bi1, and this actually, yeah, okay. Now these values correspond to the slopes so correspond to the m and b of the ith tangent line at x tilde 1. So that first tangent line. Okay, so what we're saying is our function f of x has to be greater than the tangent line mx plus b. Right? Now, because we use multiple tangent points, we're going to repeat this process for each tangent point. So now we do it for the second tangent point. Right? Where again, M and B are calculated according to the tangent lines, right? So this is at x1 tilde. Here we have M2 and B2 at x2 tilde, right? And this process repeats. So each tangent line is associated with an M, a B, and a tangent point x. Now that tangent point x is not the same x here. The x we're referring to here is the decision variable that's part of the optimization. Now we'll repeat this process for each tangent line. And so the more tangent lines you have, let's say we have k tangent lines, the better your approximation will be. Okay. Now, this also depends on where you put your tangent lines, right? There's always good and bad places to put your tangent lines. And we'll go over that a little bit more later. All right, where does this take us? Well, we have this general structure now of approximating a single separable function fi of xi. Now we can certainly, if we have multiple separable functions, then we can put this all together. So in that case, we would say let's minimize. So here I'm going to tell you, we're going to have to add decision variables for each separable function. So MATLAB or Cplex doesn't allow us to write in fi, xi. So essentially what we're going to do is we're going to represent each one of these with a decision variable. So we'll have T1, T2, T3, all the way to Tn. Okay. With that, our linear optimization program will look like the following. Minimize T1 plus T2 plus T3 all the way to Tn. And again, each one of these represents a separable function in the decision variables, right? x1 to xn. The approximation to that function will have its own set of equations. In this case, we'll have something like m11 times x1 plus b11 is less than or equal to T1. Actually, let me write it the other way so that it sort of looks like what we had before. So we can say T1 is greater than or equal to M11 X1 plus B11. And this will repeat for each of the tangent lines. For this particular formulation, I'm going to assume that we have k tangent lines for each separable function. Okay. So this set of equations represents the approximation for our first separable function in terms of x1. Now this gets repeated for every dimension of the decision variable. So for the next set, we're going to want to represent an approximation for f2 on x2. It's going to use a similar idea. So, but now instead of t1, we're going to have t2. I'm going to assume that the number of tangent lines to approximate f2 of x2 is, again, k lines, but it can actually change. So depending on the function, sometimes you only need 3 or 4 lines to approximate a function pretty well. Other times you might need 10 or 12. So it really depends on your problem. You kind of just have to figure that out through trial and error. Oops. So now we have m21 x2 plus b21 m22 times x2 plus b22 Now we have a set of constraints to approximate our second separable function. This process repeats over all the dimensions that you're trying to linearize. Okay. So in our case, if x is of n dimensions, we could have up to n sets of equations for each approximation. Here we have an approximation for the function f of n in terms of x of n. And there we go. Now you might be asking yourselves, well, how do we calculate these m's and b's? The process is pretty straightforward. So, I sort of think about it in terms of 3 basic steps. Our first step is to select the points where we want to make the approximation on a function. So here we're selecting xi tilde, where tangent lines are, let's say, calculated. For the nonlinear function. After that step, in order to calculate the tangent lines, we're going to want to first calculate the slope, and this is probably the easiest. And we do this just by calculating the derivative. And this derivative is calculated for each of the tangent points. Okay. I should probably write xij. So we're going to calculate the derivative of the function f of I for each of the tangent points. And again, if we have k tangent points, then we're going to calculate the slope or the derivative at each of these tangent points. This will provide us with each mij. Or more specifically, mij is equal to the derivative calculated at the tangent point. Okay. So now we have our slope. Our next step is to calculate the y-intercept for each tangent line. Now you can certainly, for those of you who've done this before, it's not too bad. Maybe you can calculate it on your own, but I'll sort of provide the equation. That way you don't have to go through the calculation. So if we have a point here, and again, we're going to put a tangent line through the function. We want to calculate this point right here, the intercept. It's pretty easy, so we're going to begin by figuring, we know the point there, which is xij, where we're taking our tangent point. We know the corresponding y. At f of I tilde xij. Now we just need to go backwards and up according to the slope. I'm not sure what just happened. In this case, if you work out the math, Bij is given by fi x tilde ij, and then we're going to subtract off the slope times the distance from x equals 0. That will give us the y-intercept. At this point, we now have everything that we need in order to perform our linearization. Okay, let's actually do this with a problem so you can see how it works out with separable functions and selecting your tangent points and whatnot. Oftentimes, these calculations are much easier to do in Excel, and this will become helpful when we start tying this into Cplex, because we can just load in our Excel calculation. All right, for the example problem, we're going to say we want to minimize an unconstrained function 5e to the negative 1/2 x1 plus x2 squared. Now, for now, we're going to ignore the fact that Cplex can handle a quadratic. We're choosing these functions just to make our lives a little bit easier and to demonstrate this approximation method. The first thing that we're going to want to verify is, in fact, that these two separable functions, right? So here we have f1 of x1, right, is equal to 5e to the minus 1/2 x1. So that's separable, right? It's only in terms of one variable. And then here our second function is f2 of x2 is equal to x squared. Right. What do these look like? Well, the first equation is an exponential that looks something like that. Right? And it passes through the y-axis at 5. Now you can take the second derivative. So if we want to verify convexity, we look at the second derivative. So f2 of x e to the minus 1/2 x1 the first derivative of that is minus 5/2 e to the minus 1/2 x1, while the second derivative is 5/4 e to the negative 1/2 x1. In this case, this equation is always greater than or equal to 0, no matter what x1 is, which tells us that the, and that should be 1, I don't know why I wrote 2, that the first function, first separable function, is in fact convex. We can go through a similar process with the second separable function, right, where we take the first derivative, we get x, and then we take the second derivative, and we get 1. And clearly that's always greater than or equal to 0. So the separable function, x2 squared, is also convex. But we could tell that visually, and if we were to plot them, we'd go, oh yeah, that definitely looks convex. Okay. Now for this particular problem, we're going to add in a couple constraints, although this isn't necessary, but sometimes it happens. Let's rewrite our problem. And we're going to have just a couple constraints that put bounds on x1 and x2. So we're going to say x1 is between 6 and negative 6, and x2 is between 10 and negative 10. Now these are arbitrary bounds, but we're picking it nonetheless. All right. But our goal here is to understand how we can linearize the objective function. Now what we know is kind of where we want to go. In the process of linearizing, and again, this is approximate, so they're not going to be, our representation will not be exact. So maybe we should just write this one direction, I guess, and just say, it's approximate. We're going to end up with an LP that looks like the following. So minimize T1 plus T2, where T1 is going to be an approximation of the exponential part, while t2 is going to be an approximation of the x2 squared, the quadratic. With that, we still have our constraints on x1 and x2. So we bounded them by 6 and -6 for x1. And then for x2, we bounded them between -10 and 10. We're then going to have a series of approximations for the exponential and for the quadratic. And these are going to map back to the t1 and t2. That means we'll have t1 times x1 plus b11, right? And depending on how many tangent lines we have, we will have that many corresponding linear constraints. In this case, I'm going to, again, assume we just have k. And, you know, there's no need for the number of tangent lines to match, oops, and this should be 1, to match for each function, but I'm going to write them so they both have k tangent lines, but you don't have to do that. So again, this is going to be an approximation of 5 to the e to the -1/2 x1. We also have an approximation for the quadratic. And I switched the index here by accident. Again, this is for x2 squared. Now what I'm going to do is pick a set of points that we're going to approximate the exponential and a set of points that we're going to approximate the quadratic. So maybe for the x tilde of j, we're going to use the following points. So we'll use -6, -4, -2, 0, 2. Actually, I can write this sideways. So that will give us 7 tangent points. For the other function, the quadratic, was second quadratic, we'll use -4, -2, -1, 0, 1, 2, and 4. There's an important thing to note, which is these, again, they don't have to be the same tangent points, right? These are completely different functions. We don't even need the tangent points to go, in the first case, we went from -6 to 6, but in this latter case, we only go from 4 to -4. There's nothing that says we have to go all the way out to 10, right? Part of this is a little bit of an art and a science. Right. Moving over to Excel, I'm going to do all the calculations for each of the functions. So I'm going to open up a new notebook. Right. And I'll do this in 2 separate parts. So the first part will be for the exponential equation. Then we'll repeat this process for our second separable function, which is x2 up 2. Okay. All right. And doing this calculation, we're going to have our tangent points. We'll calculate our m, and we will calculate our b. So for our tangent points, we have -6, -4, -2, 0, 2, 4, and 6. Our first job is to calculate the slope at each of our tangent points. Now we already have that equation. It was just given by -5 divided by 2 times the exponential of -0.5 times whatever our tangent point is. Here we see -50, and we can apply this to each of our tangent points. So I'm going to drag that down, and that will apply the equation. So now we have the slope for each of our tangent points. We can then calculate our b. Now, if you want, you can do the little interim step. So interim step might be calculating the function at. So this might be f of x. Okay? So we could certainly do that. That will make our life a little bit easier. So here I'm just calculating the value of the function at the tangent points. Now we can apply our equation for calculating the b's. In this case, it's just equal to our function evaluated at the tangent point minus the slope times the location of the tangent point. All right, so we got -200. And again, we can sort of expand that down. We can repeat this process for our second separable function. So I'm just going to copy it over, but we're going to have to update all of our equations. Here, the first one is we're going to take the square. So we're going to map that out. Next, we're going to take the derivative, which is just 2 times 2x. Map that down. And finally, our b equation actually stays the same because it references back the calculated value of the function at the tangent point and the slope. So we actually don't even need to change anything here. What we do need to change is we did select a different set of tangent point locations. All right. With that, we actually have everything that we need in order to write an LP to approximate our original problem. What I'm going to do is copy this over to the OneNote. Put it over here. And there we go. Okay, at this point, we can write out the linear program. We can put it all together. So we'll have minimize t1 plus t2 such that x1 is greater than -6, x1 is less than 6, x2 is greater than -10, x2 is less than 10. And now we're going to write out all our equations for the tangent lines. We'll have t1 is greater than negative 50.2. You know, I'm not going to write the whole value out, but essentially we have these m values times x1 plus the corresponding b's. So here we have minus 200.9. Right. And we're going to go through each of these. Again, I'm not going to write these down perfectly, but hopefully you understand sort of where I'm pulling these values from. And this process repeats for each of these tangent points, right, until we get down to minus 0.12 x1 plus 0.996. Right. Now these, again, these sets of equations approximate 5 times the exponential of 1/2 x1. We then repeat the same or similar set of equations for the quadratic, and we can just pull in the values from the table that we've calculated. And again, I'm sort of skipping some because I don't want to write all 7 of them down, but hopefully you can follow along. Now in this case, notice we don't have a requirement of non-negativity, right? We're actually allowing x1 and x2 to be negative. At this stage, you know, if you wanted to formulate it in matrix form, you could certainly say, well, let's minimize C transpose Z such that AZ is less than or equal to B. You know, our Z would be given by our X decision variables, and then we're going to have our T decision variable. So for this particular problem, it would be X1, X2, and T1, T2. Okay. Now our C transpose, well, with that in mind, our cost is only calculated based on T1 and T2. So our C would be something like 0, 0, 1, 1. Now A and B get a bit more complicated because we have to maintain all our prior constraints along with the constraints that we've introduced as part of the linear approximation. Now, that said, we can sort of figure out a pattern here. So what's the pattern look like? Well, if we remap everything, we have Ti minus M, let's say Ij times Xi plus B. Oops. We're going to keep all the constants on one side. Bij. Now we want to actually flip this inequality. Usually it's a better idea to have your constants be the less than. So we're going to multiply everything times minus 1. Okay. So with that in mind, we can actually figure out what our A and our B matrix look like when we linearize our functions. In this case, our A is going to look something like the following. We're going to have M11, M12. In fact, if you want to think about it, so we're going to make this big matrix. Right? We're going to have a vector of all the m's that approximate the first function. So I'm going to sort of make this bold, and I'll say M1. Okay, and this is M1. Again, It's a vector with m11, m12, all the way to m1k. Right. That will allow us to capture this guy here. We then need to get in the ti. So we'll have the value -1, right? For that specific ti. I'm going to move this over. And for the b, we see that we have bij there. Okay. So again, I'm going to write this as vector b1. Right. And b1 is going to sort of follow a similar pattern. So it's going to store all the intercepts for the linear approximation, or the tangent lines, to that first function. Okay. Now, if we have multiple dimensions, so this is for x1 and t1. If we have an x2, then we're going to have another m, but this will be for all the slopes for x2. So we have that for the problem above. Then we're going to have -1 for t2. And we'll also have a b2. And this is going to repeat for each separable function. So if we have n decision variables, each with their own function, then we're going to have n of these b vectors, right? And this can go all the way to xn, and this will go all the way to tn, in which case we end up with m n, and this will go all the way down to -1 for the tn. Everything else is going to be 0. Right? So that will give you your A and your B matrix. So it's a nice little structure, right, that we get. If you want to get a sense of the dimensions, right, so if we have n decision variables, each with k tangent lines, then the number of rows will be n times k. Right? In terms of the number of columns, it just corresponds to our number of decision variables. So if each decision variable has its own objective function that's separable, then we would have 2n columns. Alrighty. Now for this particular formulation, we discussed functions that are separable. So in terms of fi, xi, that were convex. Now, that's not to say you can't actually apply this procedure to more complicated convex functions. So you can have a function that's convex in terms of 2 variables, right? It just becomes a little bit harder. So let's say, oops, that's bad drawing. We had something like this. Right. You could certainly approximate this, but what you'd have to do is you'd find a set of planes, right, at various tangent points, okay? And you have to make sure that you get all the tangent points. And the problem is normally people don't do this because figuring out how many planes you need will determine, you know, it's not so hard to figure out how many tangent points, right? Basically, you have this curse of dimensionality. Normally, let's say you only needed 5 tangent points in the, let's say you needed 5 for each function here. Okay. When you do stuff like this, what's going to end up happening is you're going to need, you know, it's not just like 5 tangent points for one function and 5 tangent points for the other function, so for x1 and then x2. In fact, what you'll probably need is something like 25 tangent points, right? If you go to 3 dimensions, you'll need 5 times 5 times 5, right? So it scales up very quickly. So normally that's why we don't do approximations in multiple dimensions, but you absolutely can. All right, so this gives you an idea of how we can approximate nonlinear functions. Later on in the Cplex videos, we'll actually do this using Cplex so that you can have a good example of how to do it.